Okay, I think everything should be all set. Let me just check. Yes, registration recording started, and therefore we can start. So, how are you? Okay, decreasing in number, this is expected. However, first, an important announcement. Next Monday, the lecture is canceled because I cannot teach, and also my colleagues, neither of them can teach. So it will be recovered later. I will update the schedule on my website, but not in the official timetable because it takes a bit of time. So I cannot really make a change there. Just note that, and I will send an email to you through Virtuale, and I am sending a message in the chat of Teams just to remind you. And in my website, I will cancel the lecture. For those who just came, next Monday lecture is canceled because neither me nor my colleagues can teach next Monday. And in my website, I will update the calendar and I will add the date when the lecture will be recovered. So just be aware of that, okay? I'm sending the warnings, but in my experience, it's these changes sometimes are not got by the students. Okay. So just a quick recap to summarize where we are and what we are doing. We made a short introduction on climate change and major consequences, major impacts on climate change. Now we are in the second lecture called the climate change problem, which is getting into the science of it. And the science of it means looking at the data that we can use, looking at the concepts, and looking at the forcings. So this is why we started talking about the forcings, and I will continue right now. And you will see we will also look at the data that we need. The next lecture will start getting into the models that we can use or methods for making predictions. If not models, like for instance, kind of guess estimation or other ways of developing predictions for what we should expect for the future. Today, I start by talking about forcings and feedbacks, and we will see what the feedbacks are. The forcings, let's say that the term clarifies what we are talking about. The forcing is given by the set of the drivers of the climate system. Drivers, I mean, for instance, the energy. We know that the climate system is a dynamical system which is fueled by energy. So it's a system that is continuously changing its state dynamically in response to external drivers, like, for instance, energy. So if we get more energy, we get, of course, an impact on climate, and the most obvious one is increase of temperature. If we got more energy from the sun, remember that we are talking about a closed system, the Earth system, where the only income, the only thing that can get into the system is energy from the sun. And we said that energy that we get from the sun is what moves the whole Earth system. Okay, so basically, changes in the energy that we get from the sun cause several a cascade of impacts, and the first one, the most obvious one, is an increase of temperature. Another forcing is the state and of the atmosphere, and in particular, because it's not correct to say that the state is a forcing, in particular, a forcing is the CO2 emissions inside the Earth system. And so CO2 emissions from humans is another forcing. So what are the most important forcings? There are many forcings to the climate system, but the most important ones are the solar irradiance, so the energy that we get from the sun, greenhouse gases, and other gases like aerosol dust, smoke, and soot. Solar irradiance is the power per unit area of the land surface that is received from the sun, and it's measured in watt over square meters. It's not easy to measure, so we can measure it, but there is some uncertainty in it. And it's up to now, it's impossible to predict. We know that there are some cycles in the solar activity. We know very well the 11-year sunspot cycle, but other than that, to make a prediction of the solar activity, it's not possible because we don't have the required information. So we cannot make predictions on the solar activity. We know for sure that the solar energy will come to an end, but of course this is in the very long time, and we cannot also predict when actually, but we can say it's in the very long time, and sooner or later it will come to an end. But during the period from now to the end, we cannot make reliable predictions. And actually, it's possible that there are some fluctuations, which are local cycles, that we cannot predict. So this is indeed an important driver. There is a lot of debate in the scientific community. There are a lot of debates, plural, in the scientific community about the dynamics of the solar irradiance and what will happen in the future. It is something that actually, as I said, we can even not measure in a precise way, and therefore it's impossible to make predictions. There are also greenhouse gases, but let me talk first about the aerosols, dust, and smoke. These are also matters that are in the atmosphere, aerosols, dust, and smoke, and their effect is opposite to that of greenhouse gases. It can provoke a cooling of the atmosphere because they are like a screen. They are like a screen with respect to the solar radiation, while greenhouse gases are a screen against the outgoing solar irradiance from the Earth to the space. So aerosol dust and smoke can, in a way, a bit compensate the effect of the greenhouse gases, but actually the word compensate is not a proper word because we don't have to seek a compensation between these two effects because also aerosols cause other impacts. So it's not something that that we can use in a way to manage the Earth system because, as you know, there has been a huge campaign in order to limit the emissions of aerosols because they cause like other problems, environmental problems, like the hole in the ozone screen, etc. So what about the greenhouse gases? We already mentioned that there are many of them, and CO2 is what is considered most important, but actually also methane is a greenhouse gas, and also the water vapor. The water vapor usually is not very considered because it has a residence time in the atmosphere that is very short. And also it's a natural component, and therefore, I mean, it's something that is not related to anthropization. It's not something that is, in a way, raising concerns about our future, because, you know, it is something that it has been always there, and therefore, and also the residence time that is much shorter, it is something that is not really concerning. CO2 is the most concerning because it's also related to human emissions, and mainly to the burning of fossil fuels. So let's point out a first important consideration. If we want to make predictions about the future climate, in principle, we have to know, it's necessary to know predictions of these four things. And okay, let's forget about the solar irradiance. It's something that we cannot predict, as I said. And therefore, usually it is kept constant when elaborating future climate predictions. In other cases, on the other hand, also for the aerosols, we are not concerned because there have been several campaigns to the reduction of aerosols and also to the reduction of the release of particles of dust. And there are ongoing policies that are already decreasing a lot these concentrations, and therefore they are not really a matter of concern. For the future, it's relatively easy also to make predictions because we can indeed predict with a good chance of success what will be the result of our campaign, our policies for the reduction of these emissions of aerosols and dust. Of course, there are also things that we cannot predict, like volcanic eruptions, but in general, when we develop scenarios, we don't really need, we can assume that the concentration is constant or steadily decreasing according to our management policies. So it's not something that predicting the concentration of aerosols, smoke and dust is not really something that is concerning. What is challenging is to make predictions about the greenhouse gases emissions. And this is why the research is concentrated on these gases, and in particular on the CO2 emissions. Because on the one hand, humans are responsible for them, mainly through burning fossil fuels. On the other hand, it's not easy to make predictions, especially when, okay, there are two challenges in making predictions. The first challenge is when they refer to the future. Making prediction about the past is very easy. There is a famous proverb, a famous saying, who says, making prediction is difficult, especially when referring to the future. Okay, this is a kind of course, when we say prediction, it's implicit that we refer to the future. But indeed, making predictions is not easy because we refer to future conditions and we cannot observe the future conditions. So making predictions, by definition, not easy. Making predictions about social variables is probably the most challenging thing that we can do. And you have an example every day. So making prediction about the evolution of economics, the evolution of the geopolitical situation, and the evolution of the human reaction to challenges, or even let's refer to a very simple example. Make predictions for elections is not easy, and elections change the evolution of the social dynamics. And sometimes they change the evolution of the social dynamics in a dramatic way, in a very significant way. Okay? The way the election in the United States have the way driven the subsequent international geopolitical situation is indeed very, it is marking a big change with respect to the earlier situation. And of course, with a different outcome from the elections, the situation would be different. And making this prediction is indeed challenging. So you understand that when we get into the big challenge of predicting the future climate, this big challenge entails several other challenges, sub-challenges, but some of them are really real challenges. And of course, one challenge is the models. We will see that the models are not really very, very final, meaning that they are not able to predict, even if we knew all the inputs, they are still describing some part of the climate system with uncertainty, and therefore the models are not strictly speaking correct. There is uncertainty, we already mentioned. And there is a big challenge related to estimating the future concentration of CO2 in the atmosphere. How the challenge is tackled, how it's dealt with. Okay. It's dealt with by making indeed predictions of the societal evolution, which turns into socioeconomic predictions. And basically, these predictions at the end of the story deliver a corresponding prediction of the CO2 concentration in the atmosphere. The graph that you see over the screen shows it's a graph of the prediction of emissions, okay? And it was issued, I think there are some more recent one, but not because this one was issued around 2010, so it's relatively quite recent. There are three updates, we will look over Wikipedia in a moment. And this is the prediction of the human emissions of CO2. And they start with current value. And usually we refer to at least 4 different predictions, 4 different scenarios. These are emission scenarios. Okay. Scenarios, I mean, the meaning of the word scenario. Scenarios are not real, strictly speaking, predictions. Because with prediction, usually, we mean something that will become true. So when I say, when a prediction for tomorrow is something that I will compare once I get to tomorrow with the climate, the weather variables. So it is, the prediction is something that will become true. True usually is a number that we compare with an observed number. So in climate, given that there are so many uncertainties, usually we talk about projections. And the projections are kind of predictions. It's not easy to define what they are. If you look over the web, of course, in climate science, the definition of projections is a bit labil. It's not really final. But projections are meant to simulate something that will happen, but this simulation is in terms of statistics, not really in terms of what will become true. So, for instance, when I make a prediction of global temperature is statistics. It's the average of individual measurements. And of course, you will have a number later on to be compared, but it's still a statistic. And therefore, it's not really something that you can verify with certainty with respect to an observation. So basically, to mean that climate models are not yet effective in predicting what will happen into the future, but can predict a kind of behavior of what will happen, they use the term projection. And the projections are usually formed according to scenarios. So scenarios are simulations derived through some methods, typically mathematical methods, of the forces and the variables that, when put together, deliver the projection. So we say climate projections are elaborated depending on emission scenarios. Okay? And the scenarios is a kind of what if. Like, let's suppose that we continue our business as usual in burning fossil fuels, etc. And we get this scenario, no climate policies. And you see that there is a spread, because still, even if we develop our business as usual, there are several models delivering these scenarios, these future outlooks. And then if you use one model instead of the other, and if you use all the models, you get this kind of spread, because there are models giving a lower bound, and there are models giving an upper bound, and therefore you get this spread. This is called ensemble modeling, ensemble scenario. Okay, and this is once again the business as usual. So let's suppose that we don't do anything. Okay, and then we get this emission scenario. And then there are other scenarios corresponding, for instance, to current policies. You know that there are policies for reducing CO2 emissions, and these policies actually are quite effective. And if these policies continue as we hope they can continue, there is the target of zeroing carbon emissions, CO2 emissions by, we said 2030 earlier, and then we say 2050. In Europe now we say 2050 for a carbon neutral society, for the target of getting a carbon neutral society. And there are some papers, some researches, assuming that we already reached the cap and we are at the global level and we are already decreasing. In fact, you see that this current policies curve, depending on the ensemble members, so depending on which path you follow inside this spread, they allocate the cap around, for instance, if I look at the bound, if I look at the lower bound, the cap is around 2030. This is a second scenario, current policies. And then there is another scenario which sets the target of increasing temperature, starting from the pre-industrial level to 2.4 degrees, which is lower in terms of emissions. By the way, in any scenario, you see here highlighted what is the expected warming with respect to the pre-industrial level. So the no climate, the business as usual, no climate is often termed business as usual. Predicts an increase of temperature of more than 4 degrees, a target of 2.5-3 degrees of increase. And then there is the pathway of 2.4, and then there are other two pathways, the plus 2 and plus 1.5. And of course, with the target of reaching a lower level of temperature, you have to force a drastic reduction of CO2 emissions. By the way, the 1.5 target is the target of the Paris Agreement that was set in 2015. And I mentioned to you in the past lectures that actually we are already reaching almost there to 1.5. So it was a target that was overly optimistic, of course. So we get these predictions of emissions. Okay, this prediction of emissions then feed other scenario of socioeconomic pathway, meaning that they try to put together the emissions with a general pathway of societal evolution, for instance, in terms of human population. And they try to put the two things together to get what is called shared socioeconomic pathway. It's called SSP, okay? Shared socioeconomic pathway, which delivers, at the end of the story, scenarios of CO2 concentration in the atmosphere. Therefore, we have three steps. Emissions, scenarios of emissions, which feed the shared socioeconomic pathway scenarios, which, by putting together emissions and the other drivers of societal evolution, deliver the scenarios of CO2 concentration in the atmosphere. which are called RCP. Now I'm opening a Wikipedia page because in my web pages I want to describe scenarios. I didn't make it complicated, but I believe it is also useful to give you the information related to the other subsequent scenarios. It's not something that is in place, so you don't have to expect anything related to these scenarios as a question for the exam. The only thing that you have to expect, as I already told you, is what is reported by web pages. Okay. Okay, fine. Let me open a Wikipedia page in order to better clarify. And also, it's an opportunity to give you data figures. So let me go to here, and then let me open here and emission scenarios Wikipedia. Okay, climate change scenario. Let's open here. Okay, climate change scenario refers to a scenario of climate, which comes from the estimate of the drivers. And one of the drivers is emissions and CO2 concentration. Keep in mind what the models need for the future. The models, I mean, the mathematical relationship predicting, I can't stand anymore the spam of the phone, so let's cut it off. This is really something. And what the models need, the models are a set of mathematical equations that produce the future climate. And what the model needs is concentration. Okay, so of course, in order to produce an estimate of concentration, as I said, we need to also estimate the emissions. Okay, so climate change scenario. Let's just skip this because it refers to climate, and let's skip this figure and let's get here. Okay, this is, I believe, the same figure that I have included in my web page is the same. Is the prediction is starting from 2010, and these are again emissions. Okay, so let's close this, and 1 second. Okay. Okay, this is a graph of the shared socioeconomic pathways. So basically, this graph gives again already CO2 concentration, and it's computed depending on the previous scenarios of emissions. And what you see here is 5 different scenarios. SSP again, shared socioeconomic pathway. 8.5 corresponds to business as usual. Clearly, you can associate these scenarios to those of the previous figure just by comparing the levels. Okay, so the highest level of CO2 concentration corresponds to the highest level of CO2 emissions. And the scenarios are used in sequence, and this gives already CO2 concentration. So in principle, SSPs could suffice to run climate models, and in fact, these scenarios were used up to about 10 years ago to run climate models. And then there was an evolution which I am illustrating now. Once again, this is not material for the exam, it's just for your information. So one thing is the emission, and one thing is the scenario CO2 concentration. Okay, good. Now, one important thing, which scenario should I use? It is usual practice, and the European Commission recommends it, to adopt, for making climate projections, to adopt the business as usual, because it's a kind of precautionary assessment. It makes it safer. On the other hand, it's widely recognized and accepted by the climate community and the scientific community in general that is too conservative. Because there are already policies in place, and the previous graph clearly demonstrated that there are already policies in place which makes this assumption of business as usual too conservative. And this is a bit of a problem when policy is too conservative because the costs associated with the policy to the mitigation of the CO2 emissions increase a lot, and therefore make probably these costs not affordable. And this may turn into inaction. And therefore you have to make a clear understanding, a clear separation of the situations where a conservative approach is recommended from the situation, like in this case, where an excessively conservative approach may turn into decrease of the efficiency of our capacity to get to target. So basically, the scientific community is suggesting to use the second one. Okay? Is 3.7 or 4.5. No, it is suggesting now 4.5, the third one. Okay, and which, as you see, is associated to reaching cap of the emissions. It's associated to the third of the previous emission scenarios, and therefore is associated to reaching a cap of emission between 2030 and 2050. But on the other hand, it's important to keep into account that there are some European recommendations and guidelines which suggest to use the business as usual. There is a debate ongoing on that and a discussion that is quite interesting. Now, starting from 10 years ago, in climate modeling, we started to adopt a different projection of CO2 concentration, which is called a representative concentration pathway. The representative concentration pathways describe, again, future greenhouse gas concentrations, not emissions, I'm reading here, and have been formally adopted by the IPCC, the IPCC. And the pathway describes different climate change scenarios, and depending on the emissions and what is changed with respect to the SSP. What is changed is the way the future evolution of society, not emissions, but the societal context is evolving. The way the future evolution will be shaped. We don't get into the details, but it's a change in the evaluation of the societal evolution in the next years. And you see that the IPCC began to use these 4 pathways in 2014, so about 10 years ago. Okay. I think that's it. You just have to keep into account that these emissions turning into CO2 concentration scenarios are an essential ingredient for climate prediction, climate projections, better. And of course, there is also in these scenarios of emissions and pathways, there is, of course, uncertainty. And the current evolution of the international situation, because we have to think at the global level for these scenarios and for climate change scenarios, we have to think at the global level. And therefore, in order to evaluate the uncertainty, is of course recommended to look at the global evolution of our state of society, our socioeconomic state. And the current evolution during these days confirms that there is a lot of uncertainty, of course. Well, let's go back here. And here it is mentioned also the clouds. The clouds are a forcing, which depends on the concentration of water vapor, depends on the increase of temperature. But actually, it's not fully clear how the cloud coverage will increase into the future. And making a kind of some considerations on the evolution of clouds allows me to introduce the concept of feedback. What is the feedback? The feedback is a kind of reaction of the system. So when you have a system, the Earth system, that includes subsystems, we will see that usually we decompose the Earth system in order to study it in subsystems. For instance, the water cycle is a subsystem of the Earth system, and the climate system is a subsystem of the Earth system. And the anthropogenic system, society, is a subsystem of the Earth system. So these systems are connected, of course, because they form a unique body, which is the Earth system. And you see an example of connection in the emissions. So the societal system is connected to the climate system through emissions. So there are connections, but these connections usually are two-way connections. It's not only humans increasing the emissions and influencing climate. Then the climate gives a connection back, because the climate forces the human activity. Let's suppose about a real climate worsening causing disasters. Of course, this is a way to reduce the emissions. And therefore, this forcing back is called feedback. Feedback means that the system is characterized by internal connections, and these connections are not one way, they are two ways, meaning that when we analyze them, it's not so easy like saying, okay, I increase the emissions and then see the reaction of the climate. We have also to consider the feedback. Another example is related to, for instance, the human influence on the water cycle. We know that there is an influence because, for instance, when we take water from a river, then we cause the dry out of the river. But it's not the end of the story. The dry out of the river downstream has a strong implication on the human system, a forcing back. Because, of course, there is no more water downstream, and therefore there is a reaction. These reactions, these feedbacks, hopefully can create a compensation. It's like the human body, we get a virus, and then there is the generation of the antibodies that antibodies that compensate, neutralize the effect of, neutralize the virus. It's a compensation. It's a positive reaction. Okay? And this, in terms of feedback, we would say it's a negative feedback because it means that it tends to provoke a decrease of the connection in the other way. So basically, if I have an increase in CO2 emissions, there is a link towards climate, but climate may react by causing a disaster which reduces the emission. So it's called, in this case, a negative feedback because it's negative because it neutralizes the original forcing. So hopefully, then there is a compensation thanks to feedbacks. But not always. There could be positive feedbacks. Like, let me make an example. Increase of emissions cause an increase of temperature. The increase of temperature causes a release of CO2 from the oceans, and then another increase of temperature, and then another increase of emission, and then another increase of temperature, and then another increase of emissions. So the positive feedback is concerning because it could evolve towards an irreversible decline, death of the system. So we clearly hope that the feedbacks are negative. Actually, it's a good, it's a good prediction that in the Earth system there are negative feedbacks. Why? because their system survived through a long evolution. And you know that evolution means that the resulting system is more resilient. Resilient means that the system can absorb shocks and can recover after the shock. So resilience means that there are negative feedbacks into the system. And therefore, this is a good a good conclusion about the Earth system. If the Earth system survived to the impact with meteorites, survived to human evolution, survived to many things, it means that probably there are positive feedbacks, negative feedbacks. Now, let's get to clouds. Let's suppose that the following is true. There is an increase of temperature, there is an increase of evaporation, and therefore an increase of the cloud coverage. Cloud coverage means a screen against solar radiation, which means a compensation of the increase of temperature. This is what we hope. So clouds are an important forcing, and models want to know the cloud concentration into the future. Let me see what is the next slide that I don't remember. Yes. Here are other examples of forcing and feedbacks. And you see, water vapor, we already talked about it when we talked about clouds. Ice albedo. So ice albedo, unfortunately, is something that is ice albedo is decreasing, is a feedback that is positive, so it's concerning because ice is white and therefore doesn't store the heat, or let's say it heats less than the ocean, for instance, which is it's darker, and also the land, when it's not covered by the ice, absorbs more heat, which means a contribution to raising temperature. So the result would be that the temperature increases. We have a decrease of ice-covered surfaces, which means a problem because then the Earth system absorbs more heat. It's not reflected, less heat is reflected into the space. And this is a problem. Forest greening. Forest greening is a possible positive and negative feedback, so something useful. Why? Because the increase of CO2 in the atmosphere is a fertilizer, and it's absorbed by the vegetation. It stimulates the growth of the vegetation, which in turn absorbs the forests are CO2 sink. CO2 sink means a contribution to reducing CO2 concentration. And the precipitation, again, it's a feedback, because when you get clouds and you get rain causes a decrease of the temperature of the atmosphere. We know that. So all of these feedbacks divided, look at the figure in positive and negative, and the negative one are put in blue because it means that they are environmentally friendly, while the positive ones are in red because they raise an alarm. All of these feedbacks needs to be understood and translated into the tools that we use to make predictions, together with the forcings. So we need to know the forcings, but then we are moving also towards the concepts that we need to elaborate into our prediction methods, projection methods, models. And the feedbacks are an important component. What is important to say about feedbacks? 1 second, I look at the next slide. Okay, let's stay here. What is important about feedbacks? What is important about feedbacks is that we don't know all of them. These are examples, but there are feedbacks which we don't know. I give you one example, which is the evaporation paradox or evapotranspiration paradox. What is evaporation? You all know. it's a liquid surfaces where by absorbing heat, water is converted into the gas phase. Transpiration, on the other hand, is the operation by the vegetation to convert water absorbed through the roots in transpiration, water vapor that is released into the atmosphere. Usually, in some disciplines, these two processes are put together into the term evapotranspiration, which means the flux of liquid water transformed into water vapor and released into the atmosphere. Okay. Evapotranspiration, what we believe, what we guess, is a dynamic tending to an increase with increasing temperature. So our guess is after global warming, because the evapotranspiration is increased. Actually, the measurements instead suggest that evapotranspiration is decreased, and it is measured through evaporimeters. They are instruments like a small pool of water, small pools of water that are placed in open spaces, and then every day they measure the decrease of water level due to evaporation. And actually, it turns out that it's decreased. And then a long discussion in the scientific community called the evapotranspiration or evaporation paradox. And we don't go into the details because I'm not also well informed, because there are several hypotheses that have been put over the table in order to justify this apparent inconsistency. And probably one of the most credited is related to an assumption that wind after global warming, evaporation and also evapotranspiration is not only driven by temperature, it's also driven by other important variables. And one very important is wind speed. We know that when there is some wind blowing, there is an increased evaporation, and we perceive it because it makes our perceived temperature lower, because the increase of evaporation causes cooling down of the wet bodies, and our body is wet, and therefore when there is some wind during summer, you say, okay, it's very hot, it's very warm, but basically, and therefore this means that if wind speed is decreased, in terms of evaporation, there might have been a decrease. And it's not yet clear if wind speed, like a global level, has changed. It's not clear. So this is one of the possible explanations for the evapotranspiration paradox. Like wind speed is decreased, and therefore evaporation is decreased. But this is actually a feedback, that we don't know in detail. And the fact that we know some of these feedbacks is the reason why we are precise in projecting the future climate. This is one reason of approximation. Is that our lack of understanding of some connections that may help us in sustaining the climate change. It's a good thing. It's an interesting story because it delivers the message that what we don't understand, it's not only worsening the situation, can improve the situation. And therefore, given that models reflect our understanding, our projections reflect our understanding, uncertainty doesn't only mean that our projections are not reliable. It also means that our projections could be conservative, could be precautionary. The situation in the future may be better. So this is why I think this is also good news. Lack of understanding is not always a bad news. I want to skip this and jump forth to this slide, and then I come back. What is depicting this slide? It is introducing tipping points, and there is a lot on Wikipedia. You can find a lot of it. This is another interesting consideration. What is the tipping point? The tipping point, let me see if I have a graph here. No. The tipping point, let me check. I would like to get a picture that is more effective in here. Wikipedia is more effective in delivering the concept. Yeah, tipping point. This is a problem because there is a just vendor, so tipping point. Wikipedia. Okay, here it is. Okay, this is the figure that I'm showing in my, more or less, in my slides, but let me check if there is, okay, this one. I wanted this one. I think this is the good one. Just 1 second. Okay, so what is a tipping point? This is a figure that refers to society, and it's a good thing. I selected it because the tipping points are not only a feature of the climate system, they are also a feature of the society system. So what is the tipping point? Look at the upper figure. Okay? There is a system that is in equilibrium. Why it is in equilibrium? Because it is in a minimum of some optimality criteria. Or I can say a maximum. In either informatics in general, when we say an optimum may correspond to a min or a max. Okay, and let's suppose that in this case the optimum corresponds to a minimum of some optimality criteria. So basically, this system, the blue ball, the blue circle, is in an equilibrium situation because you see if you move it like on the left or the right, then you move it, but then it goes back to the original state because it was a minimum. So it goes for the minimum. The optimality corresponds to the minimum. And that's it. So this is a system that is in equilibrium, and the system, like another many societal systems, are indeed in equilibrium because it's the result of the evolution. So their system is in a firmly, we can say, equilibrated state because it's the result of a long evolution. Okay? But then, if the perturbation, instead of being a small perturbation, is more significant perturbation, the system may get close to a state where it can choose between two equilibriums, the original one and another one. Like in this case, you understand that probably the circle goes down to the other minimum, the other equilibrium situation, the other optimum. So there are systems that have two optimums. And let me give you an example, for instance. Forests, we know that when we clear cut a forest, what happens is that you get a completely uncovered area, and then you have the growth of brushes, of small children of these trees that I clear cutted. And these brushes basically do not automatically grow up to the forest condition. They may stabilize in a new equilibrium, which is a brushed area, not a forested area. In fact, we know that when we clear cut forests and then brushes come, we need to in a way, make a selection and let only few children to survive, so they can get the food that is necessary to grow up and then prevail over the other children, so giving back the forest situation. But if we don't intervene, it may take a very long time or may be irreversible, the change to forested area to brush area. Because the perturbation is such that the system gets to the top of an hill, which means lack of equilibrium, because we said that the minimum here corresponds to equilibrium, to optimum, while the max corresponds to disequilibrium, a system that is not in an optimal state, and therefore the system can go down to a different equilibrium state, and this change may be irreversible. And this happens also for societal systems. When we get an economic crisis, we can recover from it and go back to more or less the original situation, or we may get to a completely different societal system where the economy is organized on a brand new basis, completely new basis. So what is the moral of the story? And let's look at the definition of Wikipedia. You mean here in this figure? Okay, the green. Because in this, let me see, because I didn't look at the figure in details. Agents of change, creating enabling conditions, because in this case, it supposes, this is my understanding, it supposes that the new equilibrium is a condition societal development, which may be. Indeed, sometimes we get stuck in a local minima, so local optimum, which are not favorable, and you need a huge perturbation in order to converge to another optimum, which is an absolute optimum. Because in this case, indeed, if the optimum coincides with the minimum, the ideal optimum is this one. So this is why they put green here. And in society and in society is very frequent the case where a system can get stuck into a local minimum, which is not optimal. And then you need a strong perturbation, you need a radical change. And this is also the ever-going debate in geopolitics, whether mediation is more successful with respect to a strong action, a strong perturbation. And the question is more like, do we really need a strong action, a strong perturbation, or mediation can succeed in getting to a new equilibrium state? And in this case, it is assumed that there is no consideration about the geopolitical implication. It only looks in a positive way with an optimist approach to how much we need to steer the system in order to get to a new equilibrium. This is my interpretation. Thank you for the question, because how can we start? Because typically you need a measure of optimality. And for instance, let me make an example with respect to the climate system. A measure of optimality may be maybe the global temperature. And therefore, the lower the global temperature, and the happier is the situation, the satisfying is the outcome. And then you need, for instance, to relate, and I'm striving to get an example, to relate the intensity of the forcing that you put over the circle to the effectiveness in reaching the new equilibrium. And therefore, in a way, in order to analyze this system quantitatively, you need to know, first, the position of the minimums. And therefore, you have to evaluate. So if I force this change of the system, what is the benefit? And what is the advantage? And therefore, you need to evaluate this. And then you need to evaluate what is needed to steer the system to pass the high point. Just to be clear, in my slides, the treatment is much more simplified. There is the definition of what is the tipping point, and there are some examples. If we will get back to the climate system, what is an example of a tipping point? I make you an example that is very popular, and is the presence of the polar ice caps. The Earth has been, during its history periods, actually, the longest period in the history of the Earth has been marked by absence of ice caps at the poles. And for a more reduced part of its life, the Earth had ice caps at the pole, and more than one. So there were cycles. The big question is the transition a kind of a smooth transition, or is something that may be a tipping point? Tipping point means that we could turn into our current situation with ice caps to a new situation without ice cap through an irreversible process. So the question is, this increase of temperature we are living today is, of course, decreasing the extension of the ice caps. In turn, this is causing a lot of other consequences. Sea level rise is minor one. Look at the geopolitical consequences. It's very relevant. So this transition is something that is slow. Decrease of ice caps extending more, so increasing with increasing temperature, but it is something that may be reverted by decreasing the temperature. So maybe something smooth. Smooth, I mean very gradual. Increase of temperature, decrease of ice caps. But if one day, for one reason or another reason, we succeed in decreasing the temperature, then the ice caps will recover. Or is something more abrupt, like we reach a tipping point. After that, suddenly get to a new equilibrium state without ice caps, which means sea level rise, which means a lot of other things, societal modifications that make coming back impossible unless something really independent of our will occurs, like the impact of a meteorite, because in the past maybe that the disappearance of the ice cap was caused by the impact of a meteorite. We don't know that. So basically, these tipping points are, on the one hand, a reason of concern, because clearly there is this feeling that we may reach a limiting temperature, which may be actually very close. After that, we suddenly get a melting of the ice caps. A melting of the ice cap would mean an increase of the sea level, for instance, about several meters, so something really important, especially if it happens suddenly, abruptly. And this is not impossible. Why? Because we recently discovered that in the body of the ice caps, there is a lot of water. Why there is water? Because under the pressure of the ice that is above, the water gets liquid, cannot get icy, because you know that if you put water under pressure, then the freezing temperature goes down. And we learned recently that there are some of these big lakes that are embedded into the ice caps, especially in the North Pole. And we already observed some of these lakes breaking suddenly because, of course, with the melting of the ice, the water is under pressure, and therefore suddenly it can cause what is called a glacial outburst. So the question is, how many of these lakes there are embedded in the ice caps, and what if at a certain point we reach a limiting thickness of the ice that is above in order to cause a very rapid break of these lakes and a rapid sequence of glacial outbursts causing these glacials flooding and sea level rise, and at the end of the story, the complete melting of the ice cap, because for the reduction of the ice covered area, there is a reduction of the albedo, an increase of the albedo, and therefore there is a sudden melting. This is possible. And this is one of the concerns. And this is something that our models don't consider, because we don't have any information supporting translating into a mathematical relationship, into a prediction what may happen. It's like for our personal health. There are something that we can predict, other things that we cannot predict. And of course, the human body is a very good example of tipping points, because there are unfortunately some situations that we cannot predict, which may turn into an irreversible change of our health conditions. The same for the Earth system. So these tipping points are an interesting subject of scientific research. They don't mean that, they don't imply that we have to become excessively skeptical. They just imply that we have to be aware. We have to be aware that there could be some possible evolutions that we cannot predict. And what is the solution? What could be the solution? For instance, analyzing the possible outcomes in probabilistic terms. And this allows me to introduce the role later on of statistics. Now I go back, let me see. This is an example, it's another slide of societal tipping points. Here there are a lot of examples of equilibrium situations. And for instance, carbon neutral cities may be a future equilibrium situation. Now we are in a fairly stable equilibrium situation with burning fossil fuels. And we are trying to steer a shift of the system to carbon neutral societies, and which would be another equilibrium situation. This is an example. And you know that when you put together all of these tipping points, the problem becomes very interesting and justifies the fact that climate science is, in its complexity, a very active field of research. And I think, okay, let's go back now. Okay. All of these things are related also to climate change attribution. And climate change attribution, I don't want to spend time on this because we already discussed it. Climate change attribution tries to respond to the question, who is responsible for climate change? It's natural variability, humans, it's a combination of them. And if it is a combination, what is the weight of natural variability and what is the weight of anthropogenic influence? And this is an active subject of research. And you understand that it's very relevant because if, for instance, we recognize that natural variability is prevailing with respect to human influence, then it's a completely different story. And our resources should be concentrated then on adaptation rather than mitigation. Because if we concentrate resources on actions that may be only partially effective, then it's a problem because there is lack of resources. And there are some links here, and these links are to our website, it's called Geoscience Videos. There are several videos, they are quite educational, they are not very scientific, they are educational. But it is interesting. It is interesting because they clarify what could be the role for anthropogenic force. and also the role of natural variability. This video is trying to explain what may have caused the sequence of ice ages that we experienced, and the role of climate cycles. And they are nice, especially for educational purposes. So this is why I wanted to link them here. But again, there is a long literature on this, and there is a Wikipedia page on climate change attribution. If you are interested, just look at them. We are looking at the science of it, so we are not really interested in the question who is responsible for it. We are looking at the science, and this is an overarching question, because once we better knew the science, of course, we can also answer this question. And I think I'm skipping this because it's not really relevant, and I think I am also skipping this. And because I mean, in my introduction, I already mentioned the disciplinarity of the problem and the many implications, and then this slide is dedicated to the discussion of the different roles of the disciplines that are involved in climate science. And there is emphasis here, given that I am an engineer, so my opinion is subjective. There is an emphasis on the role of engineering, which is related to the role of climate adaptation. Climate adaptation is something that is in the realm of engineering, because it means designing actions, designing also policies, which are not part of engineering, but mainly it's not only policy, it's also actions, preparedness, structures, green solutions, in order to adapt to climate change. And the reason why I am including this slide is that there is a general orientation to put more weight, and for reasons that I fully agree with, on mitigation. Mitigation, as we discussed 2 weeks ago, means reducing human emissions for trying to contrast global warming. We discussed the time scale that is maybe very long. We discussed the costs, and we also discussed the alternative, which is live with climate change through adaptation. And we made the example of air conditioning, which is not a very good example. Air conditioning has related impacts, but for instance, maybe successful adaptation policy may be to reduce our water demands for the irrigation, by optimizing the use of water for food, for instance. And adaptation, I am convinced, is very important, because for at least 2 reasons. First, it's the time scale. And the second reason is that adaptation implies a global call for everyone to give our own contribution, our individual contribution. It's a call to local administrations to take a joint responsibility in managing and reducing the impact of climate variability and climate change. And therefore, to do that, I think the role of engineering is extremely important. And it is something that today is a bit, in my opinion, underestimated. Underestimated means that then we run the risk of being not effective in reducing the impact of climate. Impact of climate that is indeed very important. We need to mitigate it. And even if we go back to the situation of 50 years ago, so before global warming, we still needed, already at that time, to get protected against climate extreme, climate disasters. We made a lot of progresses, but today we have still some targets to achieve, and therefore this is why I would like to push the role of adaptation. I think it is very important. Before moving forward, here are tipping points with data. I think this is an interesting discussion, but I would like to postpone this after the break. Before moving forward, I wanted, and also it's a way to get a bit more relaxed, to introduce the role of another discipline that I believe is necessary when trying to better understand climate and predict climate. And this discipline is statistics. When we deal with climate data observations, which are essential, and also when we refer to models, and we want to take into account uncertainty of models, there are several ways in which we can move, get to target, move forward. If we want to consider, indeed, if we want to manage climate data, if we want to account for their uncertainty, if we want to estimate uncertainty of climate scenarios, there are several methods that can be used. And I give you some tips of approaches that we are not considering in details. Fuzzy logic, for instance, it's a terminology that probably it's not very familiar to you because it was very popular about 20 years ago. Another option is machine learning, and you are very familiar with it. Another option is artificial intelligence, and you are very, very familiar with it because it's a topic. And indeed, artificial intelligence may be also machine learning consideration. Artificial intelligence to me is a synonym of machine learning. It's nothing different. Artificial intelligence is more catchy as a terminology because it implies some intelligence. Actually, there is nothing intelligent in artificial intelligence. It's just machine learning, and being machine learning is not intelligent. It's not creative. It's not even if we call it intelligence. It is we call it intelligent for two reasons. First, because indeed it helps a lot in being creative, in expressing our intelligence. It is indeed helping a lot. And therefore, it is a good reason to call it intelligence because it stimulates our intelligence. But actually, calling it intelligence, we imply that the artificial intelligence can, in a way, take intelligent decisions by itself. In my opinion, this is not possible. The intelligent decision is taken in cooperation and also creativity. Creativity, we call it creative artificial intelligence. It's not creative. It's creative if it is associated to our contribution, then becomes creative. Otherwise, it is merely a method very useful to digest a lot of information. And this becomes particularly useful because the web is becoming so large, so helpful, that it's impossible for one person or a group of people to browse the web and make a selection of the information. So selecting the information is indeed something artificial intelligence does very well. And therefore, artificial intelligence can also assess uncertainty because artificial intelligence can compare models and can say, okay, more or less the prediction is this one with an uncertainty of 90% plus minus, or whatever way is used to quantify it. This is something that artificial intelligence can do and do it very well. However, if you asked me what is the more classical and rigorous approach to deal with uncertainty, I would say it's probability. Probability is a branch of statistics. Statistics means dealing with numbers, dealing with information. This is statistics. So statistics, in my opinion, is including artificial intelligence. Probability is a branch of statistics that does a very simple thing. It analyzes numbers, information, events, and it is able to determine their frequency, their likelihood, but like artificial intelligence is. But what is the advantage of probability? The advantage is that probability can be rigorously tested. This is not possible with, for instance, artificial intelligence. You get a reply, but if you want to test it, you have to do it yourself. You have to look at the references, ask artificial intelligence, give me the reference, please, and study the paper. And sometimes you understand that artificial intelligence elaborated the information in a wrong way for the very simple reason that it's not intelligent. And therefore, this advantage of probability, that it is rigorously tested, it's a good thing, especially for an engineer, because, I cannot go in front of a judge and say, yeah, it was artificial intelligence suggesting that. Hopeless. Instead, if I say, maybe even not to say it, but instead, if I say it was central limit theorem, I applied it, and I tested it, and I tested that the assumptions were satisfied, I am done. Okay, so this is the advantage of probability. What is the disadvantage of probability? That is extremely boring, because even if it does a very simple thing, which is analysis of numbers, it's very simple. Like to try to estimate what is the chance that tomorrow will rain, it's very simple. You can do it even by looking outside, and you get more or less similar results. But in the attempt of giving rigorous testing, probability becomes very complicated. Machine learning doesn't do that. It's less complicated. Why? Because you have already the software ready, and you are not required, in general, to check whether you choose the right model. That's it. You say, I use the random forest. This is the reply. Cannot be defended, but still, in the application, you get a reply anyway. With probability, it is different, because you are required to make the testing, and it's the testing that makes probability complicated. But on the other hand, I would say that it's something that is really missing in state-of-the-art climate science. It's missing a rigorous probabilistic verification of projections. So this is an introductory consideration, and then we make a break. How to apply probability? So in practical terms, should I study everything? No. There are books of probability, introductory probability books, 600 pages. No, you don't need to do that. In the same way as you apply machine learning, there are softwares for applying probability, and there are softwares for applying probability testing. And you can, in a way, the solution is not harder than a solution that is based on ChatGPT. And there is no need of studying everything. Of course, you need, especially if you bring the responsibility of something you decide, you need to know what is behind the software. Because again, it's not an excuse in front of a judge, I applied the software. Doesn't waive your responsibility. Your responsibility is waived when you explain why you applied the software, what the software does, and why you think it was the right choice. And this implies some study of the theory. But you don't need to start from the definition of each component of the probability theory, go through all the theorems. This is something that indeed can be made easier by the use of softwares and artificial intelligence. And what are the softwares that can be used? In general, programming languages. It is something that when you want to analyze climate problems, in general, you don't find a ready-to-use software to make your assessment. Why? Because the amount of data is massive. It's a lot of data. So if you want, even if you want to download climate projections for Bologna uh, or supporting information, input data, now we have a lot of data available. And therefore, we need, in most of the cases, to develop tailored applications. This is also valid for machine learning. Usually, we don't have a ready-to-use software like Excel to deliver elaboration of data. We need to get into the code, making modifications, and this explains why in certain branches of science is still needed that you know how to code, how to write your own code. Because when you get to a very advanced level in your applications, in your understanding, it's clear that you don't find free lunch, you don't find anything already cooked. You have in a way to shape your methods. And this is why I always suggest to students, especially to master students, to learn coding. And for two reasons. The first one is what I already mentioned. Sometimes you need to shape your computation yourself. You cannot use something that is ready. And the example that I make is Excel. Try to analyze 1 million of numbers with Excel and you see what is the result. It becomes lengthy, it becomes, in some cases, impossible. Therefore, you have to learn something different. This is the first reason. And the second reason why I suggest to learn coding is that this helps you in understanding the concept. It may look like something that is not true, like even when I apply Excel, I understand the concepts, but actually my experience is that when you use a software that is already cooked, you are really tempted to skip the learning behind it. And while if you have to, in a way, get into the code, modify it, you are forced to learn. And at the end of the story, in most of the times, I found that this becomes very exciting. So it's a forcing, but not a forcing that becomes tedious, that becomes very nasty. It's a forcing that translates into a personal growth. And this is why I always tell students take this opportunity, because once that you get in the job market and you get into your job, is much more difficult. You don't have time. Now it's relatively easy to get into coding, to make an effort to go beyond Excel, Word, and even beyond MATLAB. But MATLAB is already a good example of coding, because those of you who have experience in MATLAB know that using MATLAB requires a lot of additional expertise with respect to using Excel, for instance. Okay, let's make the break. And in 15 minutes, we meet again here. Thank you. Oh, so we mentioned softwares, coding. There are a couple of things that I wanted a couple of information that I want to deliver to you about coding and about software. So coding means that you make computations with the PC, and you make these computations by using a software that you have developed, and it's not a software that is ready to use. Essentially, it's a computation over the PC, and most of us use as operating system Windows. What is the operating system? An operating system is an interpreter between you and the machine. It is a translator that translates to what you write on the keyboard and your movement of the mouse to the machine in a way that is understandable by the machine, so that when I move the mouse, the machine displays an arrow over the screen that is moving. And there are three main operating systems that are used nowadays: Windows, Linux, and Mac. Most of us use Windows. Windows is just an interpreter. Windows is what you find here over this machine in the room. Okay, let me just skip. I wanted to minimize all the windows, but it's too long. So Windows is what is in this PC. It is the most used. Why? Because it's very user-friendly, and also was developed with a strategy that was indeed successful, both in commercial terms and both in providing something that is ready to use. And indeed, Windows made the computer accessible to the large public. It was not always like that. When we started our experience, of humans, with the computers, the first interaction was through through cards with the small holes, and the card was the interpreter. So when we wanted to make a computation, it was translated into the language of the machine through these cards. And then other interactions were proposed, which were more user-friendly, but still up to about 30 years ago, the interaction was not easy, because it was required also an intervention of the user through coding. And then Windows developed, and now we can interact with the machine by using Windows without any need of coding. There is no need. Alternative, Linux or Unix operating system. I think it's there must be something related here. Yeah. The most popular is Android, actually, followed by Windows, and then this is Mac, and Linux only 1%. What is Linux? Linux is an operating system that is much similar to Windows. Actually, it looks similar today because the interface is very similar to that of Windows. Originally, Linux had an interface that required a massive intervention through coding by the user. Now is completely user-friendly. So what is the difference between the two? Apart from the fact that is the share. The share is 1%, and Windows has like 30% of the computer, more than 30% of the computers worldwide. The difference is that Windows is commercial and Linux is open. It's an open software. It's free. It's completely free to obtain, free to modify. You can modify it in any way. And this comes with some advantages because it's easier to adapt to your needs. But of course, you need to know something of coding. And another interesting feature of Linux is that it's basically free of viruses because of the limited share. And also it is very well protected. And this protection doesn't require any computational effort by the machine. The result is that Linux works well also with old PCs. If you try to install Linux on a PC that is 20 years ago, it works like a charm. Windows doesn't work anymore. There is no way of making it working. And also it's faster. It's faster. And being open, it's easier to find software available open source over the web that you can install without paying any fee. It's completely free. For these features, the fact that it is more efficient and the fact that it is more diffused in science for the availability of free software, it is widely used in the scientific domain for making complex computations. So if you want to run a climate model under Linux, is relatively easy. I have a web page on my website, which is top front. Run your own climate model, but this needs Linux. It's with Windows, it's much more difficult. You need to make the model very simple if you want to run it over Windows, and I'm not sure that there are the codes available. So what is the moral of the story? 90% chance you are a Windows user. Why not learning Linux? This is something that you could put up front in your CV. I know the Windows operating system, Linux operating system, and once that you know Linux, you also know Mac, because Mac is in between. It's commercial, but it's borrowed from Linux. And I tell you, it is something that is in the CV is a distinguishing feature. It's not difficult. The only thing you have to do is to install it over a PC and try it. And you'll see that it's extremely simple. Linux has several distributions. Usually I use Ubuntu. But you can use the other distributions that are shown here. There is not much difference. Ubuntu is the more popular. So I use this. Okay, Mac, I'm not spending much time because Mac is a commercial version of Linux. Same advantages, same features. It's safe. And I think it is a very good option. And but once that you know how to use Linux, moving between the two is easy. So don't hesitate. And then once that you have chosen your operating system, what is an ideal software for managing 1 million of data? Because Excel, we said, it's not a good option. A good choice may be MATLAB. I think that you already know MATLAB because it's widely diffused and you have a free license at the University of Bologna. You can download it and get it until you are a student. And it is very, very good. I don't use it. What is the reason? Because I started with a different computational software, which is open source and free, and therefore I never felt the need of learning MATLAB. And MATLAB is expensive. So until you are a student here, it's no problem. When you are not a student anymore, it costs some money. And therefore, especially if you want to extend it. And therefore, this is why I don't suggest to students, if you have to start from scratch, to start with MATLAB. What could be a good alternative to MATLAB? Or let's say it's not the correct thing to call it an alternative. It's a second solution, which is free and open source. This is my suggestion, rproject.org. Okay, if you Google this, the R project for statistical computing, you get it. It is, I highly recommend it because it's extremely powerful, produces a lot of nice graphs. Installing it is very simple. I show you. Download CRAN. It's the only link. You have to choose a mirror. A mirror means a public domain internet address when you can download it. Let's take Austria, but doesn't matter. Download R for Linux, Mac, Windows. Let's download it for Windows. You just need to select the base. Download R for Windows. Several clicks, but it's quite easy and quite quick. And then once that we get it, you just have to double click on the executable. Okay, it's working. Okay, let's take it in English. Everything is recorded here, so if you want to repeat these steps, you can just look at the video. I'm just accepting all the defaults, okay? And this is another piece that I suggest you to add to your CV, either MATLAB or R, or both of them, because they are very similar. Of course, there are some tiny differences, but remember, the programming codes are as the languages. The first language, besides your native language, is difficult to learn. The third is easier than the second. The fourth is easier than the third. The same for coding. The first language is not easy to learn, but the second, the third, the fourth is just an extension. Before I start the program that I just installed, I want to make clear a distinguishing feature of these softwares, MATLAB and R. They are platforms, meaning that we are not talking here about coding from scratch. We are talking about coding from a pre-cooked recipe. So there is a platform that helps you to code. Coding is another story. If you want to start coding from scratch, there are other options. These are platforms helping you to code. And essentially, the help is not substantial, meaning that it's a big help in terms of efficiency, in terms of your time required to learn, things to learn, but it doesn't help you in avoiding to learn the concept. You still have to code. So it is an help that is, in my opinion, efficient because it doesn't imply that you lose something in information. If you use Excel, it's different. Because Excel does much more, does things pre-prepared until the final plate that you eat. This is only pre-cooking. And Excel, in preparing everything, doesn't allow you to ignore the recipe. Here it's pre-cooking, but in order to get the final cooking, you need to look at the recipe and then learn the ingredients, what are the allergies, potential allergies, what are implications. With Excel, you don't know the ingredients. It's different. You get something completely cooked, but you don't know the ingredients, you don't know a lot of information. I hope I was clear in making this example. And I am spending some time because I believe this information is extremely useful for you, because as I said, it's a good piece for your CV, okay? Independently of what you want to do in the future. Of course, if you want to take a PhD after your master, then if you can write, I am very good in coding, then it's an asset. It's a very important asset. But also, if you get a job in the industry, if you get a job, whatever, being able to add something to your CV is important. Okay, just to close this, let me start this program then, okay? And just 1 second. I have to find. Okay, good. R. Let me look at here the menu, and then somewhere here there is R here, okay? So this is a console that is open by this program, and let me just make the font larger. This is a console. What is a console? Is a platform that is waiting for your input, and therefore it is less user-friendly with respect to Excel. It waits for a code, but the code maybe is also very simple: 2 + 2, and then return. I get 4. 2 × 4. Sorry, 2 × 4. Return. I get 8, and the console also allows me to make plots. Plot 1. This is a plot of 1, 1. You see the point here in the middle. And these plots are very nice. You can obtain very nice plots. Of course, you have to learn how to do that. You have to learn how to code. Okay. Okay, good. Let's, for now, to close here this parenthesis, and I tell you later on, I will also propose you a very simple exercise. And if you go to my web page here, there is a box here, box, computation of statistics and use of statistical software. Here there is everything, how to download R, and there is also an example of a very simple code for plotting, for instance, a temperature time series, and compute the average, the standard deviation, very easy statistical computations. So if you want to make an experiment, you can start from here. It's on my web pages, and this is my lecture. Good. Let's go back to my presentation. Here we are, climate data. So after having had some information on the software that you can use for analyzing the data, and once again, a good motivation for referring to a software is the large amount of data that we need to deal with. Now let's try to have a refined look to the data. The data are essential in order to understand and in order also to construct models. Therefore, data are essential to make predictions. The problem is that data is an essential element of the scientific method. The scientific method is based on experiments. So basically, the way we do science is to observe, to make assumptions on the explanation of what we observe, So we observe rainfall falling, and then we postulate, we assume that water comes from clouds which were originated by water vapor. And then we construct a theory to predict rainfall, basing on the assumptions that we have made. And the theory typically refers to our understanding of the processes. In the case of rainfall, it's mainly physics. And then we test the theory through an experiment. So we make a prediction, we measure rainfall, and we compare. This is an experiment. This is the way the history tells us that Galileo verified his theory of related to the falling bodies in the void. He went on the Pisa Tower, measured the time, etc., time taken by small balls, iron balls to reach the ground, and then he compared what the theory suggested to him through gravity acceleration with the measurements. And then this is how we check the theory. And also this is the way we should test also our scientific deductions about climate. But we need data. Data is a way to make the experiment. And unfortunately, the problem, and now I come back to the problem, I go back to the problem. The problem is that sometimes we lack data because for some reasons, humanity didn't think of observing and recording climate variables until the very recent past. There are only few exceptions, like the Egyptians, they measured the level of the Nile River for about the annual maximum for about 600 years, because they understood that they needed to improve their knowledge of the dynamics of the floods of the Nile River. Why? Because the floods, as you may know, were delivering fertilizers through the mud to their agricultural fields. And therefore, they realized that they needed to make predictions of these floodings, and then they built a measurement, a staff is essentially a measurement called a measurement instrument, called the Nilometer, where every year they recorded the max level. And this was for about 652 years, if I well remember. And this is an example, but it's a very isolated example. Otherwise, measuring rainfall is very simple. You just need a tank to put it outside and every day go there and see the water depth, measure the water depth that is there, empty the tank and put again the tank there every day. It's very simple. This is still the way we measure it today, more or less. And but humanity didn't have the feeling, the necessity to do that. And therefore, we started only about around 1600, so 400 years ago, so 400 years ago. And in Italy, we started measuring it. Because we realized only 400 years ago that rainfall was extremely important for forming the river flow and therefore delivering fresh water. In the past, we were not so aware. And therefore, our data about climate, also temperature measurements, they date back only to 1850, as we discussed. And therefore, we have a very little knowledge of the past climate. This is a problem. And then we have to find solutions. Why it is a problem? It is a problem because in climatic time scale, 400 years is nothing. It's like 1 minute of our life, or maybe less than that in climatic time scales. Because climate is affected by cycles that may last for 1,000 years or more than that. Because if we see glaciations lasted for thousands of years. And therefore, knowing only 400, it's nothing. It's really nothing. It is like predicting my health on the basis of 1 minute of observations of health indexes over humans is nothing. And so we have the problem of checking, finding other ways to understand the past climate. Well, there is to say that there are some climate variables that are easy, like temperature. It is easy because it's smoothly varying in time and space. Other variables are much more complicated. Rainfall is much varying. So what is the solution? What is the alternative solution to find climate data? And let me see. Okay, sorry. This is an example of rainfall observation in Bologna. It is a lucky story, this one, because it dates back to 1813, which is it is a long time in terms of rainfall. The longest rainfall series in the world, I'm talking about daily rainfall, is the one observed in Padua, started in 1725. Bologna started in more or less the same years, but then there was a break. And from 1813 it continues. Here you can see a graph of the annual rainfall in Bologna. First of all, just I think I already showed it, maybe. I'm not sure because I'm teaching two courses dealing with climate, so I make a little bit of confusion. My apologies. And it is the order of magnitude, you see, is around 700 millimeters, 0.7 meters per year. And it's important to get the order of magnitude. On average, the global rainfall is about 1,000 millimeters, 1 meter on average. And at the equator, we have the highest rainfall. I think it is about 3 meters. And then there are some dry areas. And these dry areas, the position of the dry areas varied during time. In Italy, in the south, we have about 500 millimeters. And in Friuli, it's the most rainy region, is 2.5 meters per year. In Bologna, it is around the Italian average, around 0.7. What you see here is that the overall trend is stable. There is an overall stability. There is no big change in the annual rainfall in Bologna. What you can see is in gray is some long periods with less rain than usual, more in the past than today. Today, the last very important drought was around 1950 in Bologna. So this series, which is a lucky one, shows you, anyway, if you look at the behavior, you understand that we would need much longer observation period in order to understand some more of this variability. This is natural variability. And you see that understanding it is complicated because there are up and downs that are very pronounced, very significant up and downs, and very significant anomalies, dry period, quite rainy periods. So it's a good example. And it's a good example also because it's, it's a very lucky one, as I said. Now, what is the alternative then to observations? And I'm sure that you heard about tree rings. Tree rings are a kind of proxy data. What does it mean, proxy? You can understand from the terminology the meaning. Proxy means that you don't have an observation of rainfall, but you have an observation, a number of a related variable. In this case, is the tree ring width. Fortunately, we have trees that lived for about more than 1,000 years. And therefore, we can get tree ring data up to more or less the year 1000, so about 1,000 years back in the past. And of course, you understand that both the width of the ring and the composition of the ring deliver information on past climate. In general, the larger the width, the more the rainfall and the higher the temperature, because it means favorable conditions for growing. By also looking at the isotopic composition of the ring, we can get information on rainfall. So, in principle, this proxy data, and tree ring are just an example. There are also other data like, look at the figure here, ice cores. ice cores deliver a lot of information, in particular on the atmospheric composition, because the ice was formed after precipitation that collected elements from the atmosphere and therefore deliver information about atmospheric composition. Isotopes, for instance, are embedded into ice cores, but also dust, particles of dust deliver information, for instance, about volcanic eruptions. So these proxies indeed are an essential piece of information. Also, another important proxy is given by limnology, sediments in lakes and also sediments in the seas. This is why we have several cruises operated by research programs to take cores from the bottom of the ocean, on the ocean floor, and these cores are very deep into the ocean and deliver important information. In this way, by also putting together information from several proxies, we can indeed get an indication of past temperature, first of all. But not only that, also rainfall can be detected. So you may think, well, the problem is solved. I can live without observational data. Unfortunately, there are limitations, as you can imagine. There is uncertainty, and also there is the lack of fine time resolution. I mentioned earlier daily rainfall. Daily rainfall cannot be detected through 3 rings, and 3 rings give an annual indication. And then there are methods that are being explored for getting seasonal indications, but it's already quite uncertain. So there are limitations, but indeed these data are delivering essential information, and you can get the importance of it if you make a Google search for paleoclimatic data. And there are several links. There is for sure a Wikipedia link, but let's look at the NOAA, the National Oceanic and Atmospheric Administration, because here there are interesting links for looking for paleo data. And if you look at this launch search tool, there must be somewhere. You see here, and advanced, there is climate forcing and fire history, ice cores, insect. This is another, let me clear it. Insect and lake levels, paleoceanography, paleoclimatic modeling. So let's look at 3 rings, sorry. 3 ring, okay, search. And it gets to you to a lot of data, like 1100 year El Nino reconstruction. El Nino is an indicator of the state of the global climate. You heard of it for sure. It is associated to occurrence of floods and droughts in the South America, in the Americas in general. And here there is 2,000 years tropical rainfall reconstruction and many other. And there is also here a map. It takes a long time to load, and now it is taking a bit too long. But here there is a map where you can find the location of proxy data. Let's see if I make a... It's taking, I experienced this problem other times. It's taking a lot of time to load. But the message that I would like to deliver is that if you are interested in these topics and you may look for a topic for your thesis, there is a lot of open information about climate data which can be used. And this open information, in order to make a meaningful contribution for a thesis, need to be analyzed and not only presented. Analyzed, but you can analyze it because if you have just a little knowledge of software like MATLAB or R or whatever, it's not so difficult, and it's an interesting information. And I want to show you an example of a study that I recently developed, because just let me this one. This was a study that aimed to reconstruct the Po River flows since the year 1100. I am much interested. It's internet is taking today a long time, but yeah, I am much interested in analyzing the Po River dynamics, because the Po River is essential for water resources management in the north of Italy. In the Po River Valley, it is produced 60% of the in gross domestic product of Italy. So understanding the regime of the Po River is extremely important. And what we did here was, let's try to use 3 rings to reconstruct the Po River flows in the past 1,000 years. And this is something that has been experienced several times in the United States. In Europe, for some reason, it's not a popular research topic. The reason is that in Europe, there are less data, 3 rings, I mean, and the correlation between the 3 rings and the river flow is more difficult to establish. It's not easy. But in this case, it was quite satisfactory, the result, and I can show you here one of the figures. This is a reconstruction, and let me open it. A reconstruction and prediction from the year 1100 to the year 2100 of river flows. And let's forget about the details. What is nice to see here is the 2 continuous lines. You see one continuous line covering the whole period that is more fluctuating, and one other line that is more regular, but they indicate the same thing. It's the annual flow of the Po River, the volume of water that each year goes through the Po River, and they look similar. The difference is variability, but they basically reach the same results in terms of up and downs. What are the 2 lines? One is obtained the most variable with 3 rings. The other one is obtained with climate models that try to reconstruct the past. And the fact that they look similar means that, or let's say, the fact that they don't look dissimilar means that we cannot reject the assumptions that they represent, at least in terms of up and downs, what's going on. And what do these data tell us? That for some reasons in the past, also in the Po River, in the Americas, this has been already determined. Also in the Po River, there were flood-rich periods and droughts periods lasting for more than 100 years. So for some reasons, around here, around 1200, like it was detected in the United States, in the Americas, there has been a period of about 70 years with much low flow in several rivers. It means a drought period, less rainfall, quite at the global level for 70, 80 years. It's an important contribution to understand natural variability. What about the future? The future says, the future is only by climate models, not by 3 rings, of course. The future says that if we accept the idea that the climate models provide a good reconstructions, in the business as usual scenario, there will be a decline of the river flow of the Po River, which is predicted by 2 models, the red one and the green one. Is it true? Let's say that this is what models say. It can be true. However, keep into account, so you train your mind to evaluate the scientific outcomes. Take into account that the fact that a model is good in reproducing the past doesn't mean that the model is good in reproducing the future. Why? Because in the future it is working under the 2 CO2 assumption, so under conditions that were never experienced in the past 1,000 years. And therefore, who knows, maybe it's reliable, but this capability of the model to work in 2 CO2 conditions is not tested by this study. So, moral of the story. These are the data we are looking for. This is not my last slides. And when we, and this is what is the concept that is delivered in this slide, when we refer to data, let's look at the metadata. So the way data were collected. The metadata are providing details on how the data were collected. Why we are interested in metadata? Because uncertainty needs to be carefully considered. Let me see. The last one is not relevant. We already discussed it. So we completed the second link. Good. Questions? Okay, thank you very much. Grazie. Remember, next Monday, no lectures. I will send a message to Virtuale and Teams. Thank you very much.